Alright, so now that we've looked a little bit at what the logarithmic function is and how it undoes the exponential function, we're going to see some examples in a minute about how to be able to use a logarithmic function to solve exponential examples, but there are also a lot of properties and rules that go along with logarithms, because when we talk about logarithms, we're actually talking about exponents. So when we look at something like the log base 2 of, let's say, 64, what the logarithm is actually doing is we're kind of asking a question. We're saying, when the base is 2, what is the exponent that's going to give us the 64 that's inside of the parentheses? In other words, 2 to what power is 64? And so logarithms are exponents. We're trying to figure out what's the exponent on the base that's there. And so sometimes those are more obvious, as we looked at earlier, like a 2 to the x equals 8. Okay, in this problem we get something like y would be 6. 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64. And so the logarithm says when you have a base of 2 down here, what's the exponent on that that's going to give you the value left over in the parentheses. So when we have something like the log base 10, which is a pretty common base for us, our number system works in base 10, and so that log base 10 of 1,000, sometimes these problems can take a little bit of work, but sometimes not. When you think about 10 to what power is 1,000, hopefully that's pretty obvious that you get 3. Whereas if you have something like the log base 5 of 8, here again we're asking when 5 is the base, what's the exponent on 5? In other words, 5 to what power gives you 8? That's not an obvious answer. But that's what this logarithm is doing. So that's why it's undoing the exponents there. But logarithms have, because those are exponents, they have their own rules. And so you already know probably some rules about exponents. And we're going to kind of rewrite some of those rules using logarithms. For example, I'll give you a couple of, I'm going to call these kind of some of the smaller rules. Some rules that are still helpful, still important, but they're not quite as monumental of a result as some of the bigger ones that we're going to put over here. The bigger results over here on the right. The smaller ones would say something like the log base b of 1. And really, it doesn't matter what b is. I guess I should clarify. B is supposed to be, we'll call b a positive real number here. Okay? And if you have b to a certain power and it's equal to 1, you probably know that when you take a positive real number and you raise it to the 0 power, you get 1. And so this is true kind of regardless of what that positive b value is. Okay? Other kind of smaller results that when you think about what logarithms are doing, well, it's pretty obviously log base b of b. Well, again, you're thinking about b raised to what power is b? Well, that would just be the first. Okay, and so other things like the log base b of b raised to the x power. In other words, what's the exponent on b that gives you b to the x? Well, that would just be x. And so what's interesting is in the inside here, you see there's an exponential function b to the x, and then a log base b of that function. So you're kind of composing two functions, and you may know from other classes or from earlier in this class that when you take two functions that are inverses of each other, they undo each other and you get back the original x value that you would have plugged into the function. So these are just kind of smaller results involving logarithms. They're still helpful, they're still important, and actually you might notice that all three of these are kind of versions of this third one right here. The third one is kind of the more important of that, because you would say, well, the middle one right here is talking about the case where you have b to the first power in the parentheses. The first example up here is talking about where you have b to the 0 power, which gives you 1. So they're all kind of saying a similar thing. But some of the bigger rules will combine some logarithms together, and again, when you think about what you know about how to combine exponents. The first one is going to say that the log base b of m plus the log base b of n, we're going to take this and we have enough space here to say this is the log base b of m times n. Log base b of m times n. And So this actually comes directly from something you know about exponents. I'm going to try to kind of label this clearly, but really this comes from the fact that when you multiply the bases, when you multiply two bases together, as long as they have the same base, you would add their exponents together. The second bigger rule, I would say, is almost exactly the same as the first. It's just we're going to change some operations. So we say the log base b of m, instead of adding two logs, we're going to subtract two logs. So the log base b of m. And this is equal to, now instead of multiplying m and n together inside of the parentheses, we're going to take the log base b of m divided by m in the parentheses. And really, for pretty much the same exact reason, when you divide two bases together, as long as they're the same base, you would subtract their exponents, and that's really where this rule is coming from. The third rule might be the most useful, or at least the most used rule out of these three by most students, and it is sometimes called the power rule, or the power property, that says the log base b of m to a power of p. So you have m to the p inside of the logarithm, which actually kind of looks like one of the smaller rules over on the left. What happens is you can bring that exponent of p down in front. And a lot of times you'll see students kind of write a little arrow here that reminds them, oh, I can drop that down in front. And this becomes p times the log base b of m. And I think this is interesting, kind of an interesting rule, because there's not many times in math where you can just kind of pick something up and say, I want to move this piece over here. And this is one of the only cases where you can kind of do that and say, I just want to pick up this p and just kind of move it down in front, and that will make my life easier. And yet mathematically that works just fine here. And where this one comes from is worth noting as well, is that when you have a base that's raised to an exponent, and all of that is raised to another exponent, a second exponent. In other words, one of the common phrases that's used in that situation is thinking about when you have a power that's raised to another power, you multiply those exponents together, and that's where you're multiplying the exponents together, because remember the log is an exponent. And so these rules help us be able to kind of organize our logarithms. They also help us to be able to deal with problems that have multiple logarithms. And what we're going to see in the next example is that third problem, or that third big rule, that power property rule, that power rule, is really helpful for us to be able to solve exponential equations. All right, I want to go back to that. I'm going to go back to our finance example, into our money example, talking about a savings account. And remember that problem looked like f of t equals 3,000 times 1 plus 0.02 divided by 4 raised to the 4t. And the question was, when will there be 5,000? I think it was 5,000. When will there be $5,000 in your account? And so we could set up the problem like this. This is exactly what we did last time. And the answer should look like solving for t. It should look like being able to kind of work through. And what we did first was we divided by 3,000. And when we divide by 3,000, another way that you could reduce that and put 5/3 on the left. And this is equal to 1.005 raised to the 4t. Now, last time what we did was just convert it to the logarithmic form, and we have a log with a base of 1.005. But what we could do here is, just like sometimes when we say, let's take the square root of both sides, or let's add 5 to both sides, in this case we can take the logarithm of both sides. And so taking the logarithm of both sides of the equation is going to give us something like the log of 5/3 on the left-hand side. And this is equal to the logarithm of 1.005 raised to the 4t on the right-hand side. Now, something I didn't mention earlier is you'll notice that there's no base written right here on this log. I just said the log of something. I didn't put a base down there. And probably should mention this earlier, but when there's a log like this and we don't have a base, it's kind of understood that there is a base of 10 down there. Our number system works in base 10, and base 10 is so commonly used that when we have a log with a base of 10, we just don't even bother to write 10. It's just kind of understood that we're using base 10 when that's the case. Okay, and so now you notice that what you have on the right-hand side of the equation says the log of something 1.005 raised to the 4t. And here's where those rules come in handy. Here's where, especially that third rule, that power rule, comes in really handy, because do you remember what you can do with this 4 to the t? When you have a logarithm out front, you can take that 4 to the t, and here's where we said, oh, you can just kind of move that and say, hey, I want you to go down front. And so it does. And so we have 4 times t times the log base 10 still, and it's okay. I'm going to not write the base 10. It's just, remember that when there's nothing written, it's understood that it's a base of 10. So we have 4 times t times the log of 1.005. And then on the left-hand side, we have the log of 5 over 3. And so we can solve for t here, and I'm going to put it up here in this top left corner. You can kind of see my answer there. If you work through and you solve for t, what you can do is you can divide both sides by 4 and divide both sides by the log of 1.005. And what you're going to end up with is t equals the log of 5 thirds divided by 4. And then we also divided by the log of 1.005. And you can grab your calculator and think about and plug these in. Now you want to make sure that you're careful about your parentheses. Please make sure that you put parentheses around the whole entire denominator when you plug that in, because if you don't, your calculator is not going to give you the right answer, because your calculator reads order of operations. So you need to make sure that the 4 and the log of 1.005 are going together in the denominator. So you could plug this into your calculator and you would get the log of 5 divided by 3, and then make sure you close those parentheses, and then divided by, remember I said you need to make sure you put that whole denominator in parentheses. So denominator, 4 times the log of 1.005. Okay, and now if you close both those parentheses, you got your whole denominator in parentheses, and so you get an answer like 25.6. And so think about what we're finding. Remember, we're solving for t. T then is 25.6 years. The question was, when will there be $5,000 in my account? So it's going to take 25 years for that to happen. And so when we have logarithms, we can get that t out of the exponent and move it down front, and helps us solve in those problems where we have growth and decay that's not a bad exponent.